So in a 3-equation system, linear system, we'll, just for a little while, we'll label these as A, B, and C. The goal here is to eliminate both the x's and the y's and keep the z's, or some form of that. Eliminate the z's and the x's and keep the y's, or some combination there. Now, you can use substitution if you want, but I would highly recommend that you use elimination. So if we look at A, B, and C, is there a good way to create an equation that eliminates the x's? We could just add A and B, right? So the A plus B equation, the x's cancel and the y's cancel, and we end up with 2z equals 9, so z equals 4.5. Well, how does that help? We could plug it into all the z's, and then we'd end up with a whole bunch of xy equations. Okay, and that would work. But the general method is, in a 3-variable system, I need to know 2 of the variables in order to figure out what the third is. So now I need to figure out either what x equals or what y equals. So is there a way to figure out what x equals or y equals? If I add b and c together, so b plus c, and my x's cancel, oh, sorry, my y's cancel and my x's cancel, and I get negative 2x equals 3, so x equals negative 3 halves, or negative 1.5. And now I have a z and I have an x. Now I just plug them in. Is there an equation you would prefer? It doesn't matter. They're all really easy, but I would probably pick the middle one because it's going to change my x, which is already negative, and the y is positive, and it's going to keep my z positive. So I'll plug them in here, but again, it doesn't matter. 1.5 plus y plus 4.5 equals 3. So together, those equal 6. I subtract the 6 over, and I get y equals negative 3. So the coordinate of the intersection is negative 1.5, negative 3, negative 4.5, which means left 1.5, down 3, and away from you 4.5. That z-axis. Oh, sorry, positive 4.5. Thank you. So that would be toward you 4.5. What was your question? Yeah. Okay, now I want to show you something. The reason I've labeled the A and the B's and the C's is you want to make sure you never duplicate the information. If I calculate it, and this one worked out really easy because when we canceled one variable, we canceled another, but that's not always going to happen. If I create the A plus B equation, and then somehow later I create another A plus B equation, or perhaps a B minus A equation, or some other combination of A's and B's. If I combine the A plus B equation and another A plus B equation, I'm going to guarantee to get an infinite solution situation. Because A plus B and B minus A and A minus B are all going to give you the same information. Okay? Every A-B equation, every 1A plus, or 1A and 1B equation is going to be technically identical to every other A-B equation. So if you do A and B once, you don't want to do it again, because it's essentially the same information. It might look different, but mathematically it contains the same information. So you never want to combine two AB equations, because you're essentially creating a plane that is going to be identical to another plane, and you're going to end up with infinite solutions, even though that's probably not going to be the case. All right. So let's see. We're doing 1, 5, 9. Let's look at 13. Okay, now these are not, well, who knows? This might be not too bad, but we'll see. So again, A, B, and C. Do you see a simple way to eliminate any of the variables? So you're saying A plus B plus C? That would actually work. So Shem suggests that we add A, B, and C together. And that would work, but I want to show you what I was talking about, combining things. So if you did that, you would end up with an X and a Y, an X and a Z equation, and that would work. Okay? But let's times this by 3, and that will eliminate the Z's. So essentially, I'm going to do an A plus 3B equation. So that would be 3, 3, 3, and 12. I add straight up and down, and I get 6x minus 5y. The z's cancel, equals negative 13. So I now have an xy equation that was created using equation A and equation B. Now I need to create another xy equation. And it doesn't matter how I do it as long as I avoid A and B. So I could do B and C, or I could do A and C, or if Shem's idea works, A plus B plus C. Anything other than some version of A plus some version of B. If I somehow, let's say my brilliant plan was to divide A by 3. Then I would create an equation that's not going to be very nice, but it would still be an AB equation. Any AB equation combined with another AB equation is going to give me infinite solutions because I use the same information to create it. Does that make sense? So, do we want to use A and C? Do we want to use B and C? Or do we want to use all three of them? B and C. So times the... Right, I want to cancel the z's. I got to get the z's. I need to create... Okay, maybe I didn't say this very well. I'm going to take a 3-equation linear system, and I'm going to simplify it into a 2-equation linear system. And that will allow me to bring it down to a 1-equation linear system. And once I do that, then I can work backwards to figure out what the others are. So I eliminated z the first time. Now I want to eliminate z again. So let's multiply this by negative 5. So I'm going to do negative 5b plus c. Let me write these out. Negative 5x plus 5y minus 5z equals 20. So now I add straight up and down. Negative 3x, 3 and 5 is 8y. Z's cancel, equals 34. Now, what I've done is I've taken my 3 planes and I have shrunk it down to 2 lines. I've thrown one of the planes away, and I've condensed the other 2 planes into straight lines. Now, they're different lines, but the intersection points are going to be the same values. So if I can eliminate one of the lines and bring it down to a single value, then I can work backwards and figure out what all the other values were. So what am I going to do here to eliminate either the x or the y? Double the bottom. So that would be negative 2x plus 16y and 68. Oh, wait. That'd be 6x. So the x's cancel, and I'm left with 11y equals 55. So y is 5. Okay. So what do I do with y equals 5? So let me clean this up a little bit. So now I want to stick this 5 in either of these. It doesn't matter which one. So I heard you want to plug into that one. So 6x minus 25 equals negative 13. Add 25. 6x equals 12. So x is 2. So now I know the x and the y coordinate. Is it still called a coordinate? Triordinate? I don't know. Nobody worries about it, really. That's true. Maybe they would. All right. Now, how do I find the z value? Do you have a preference on equation? B. So if we stick it in here, 2 minus 5y plus z equals negative 4. 5, not 5y, just 5. So that's negative 3. I'm going to add that over. Z equals negative 1. Uh-oh. So 2, 5, negative 1 is the value of the intersection. Okay? So if you look at 25, 25 is nice because you're already missing a z. So for 25, we could do 7b plus c, and that's going to give me an xy equation. And I already have an xy equation. So then I could solve those two systems to figure out either x or y and then work backwards. Okay? And then 29. There's definitely something wrong with 29. There's not a third equation, so what does that mean about the system? Are the equations the same? Are the planes the same? Not quite. You'd have to be able to double it or triple it, and then it would be identical. So they're not the same. So if I have two planes, how do two planes intersect? Either everywhere, or nowhere, or a line. Is it everywhere or nowhere? No, the equations are different. If we had x minus y minus z equals 2, then it would be everywhere. Or sorry, that would be nowhere. If this were a 6, then it would be everywhere. So they intersect on a line. What line do they intersect at? That's the question. What is the intersection line of those two? Well, a line is given as any two variables, right? So if I add them together, I get 3x, the y's cancel, minus 2z equals 8. That is the equation of the intersection. Is it the only equation of the intersection? Well, what if I times the top by negative 1? Then I'd get negative 2x minus y plus z equals negative 2. And then when I add, I get negative x minus 2y equals 4. I'm interested to see what Cynthia Young says. Does she actually give equations, or does she just say infinite solutions? Where is it? Okay. So we'll just be satisfied on 29 that there are an infinite number of solutions and we can find what the equations are. She references A, but we don't need to. So that'll work good enough for us. Now, I'm going to warn you, there's a much easier way to do this, which is why we didn't do many of these problems. Tomorrow, we're going to do this again the easy way. We'll do different problems. It's good to know. Okay, good luck.